Welcome to Kaleido's another episode of Tech Tuesday. We do this every week to show a full range of topics. Some of them are focused on our product features. Kaleido is a very rich platform for building anything related to blockchain as the enabling technology. And we have a very rich catalog of features, not just a blockchain itself as a service, but a lot of components that are very useful for building decentralized IT systems. We also try to introduce interesting technologies that we observe our customers adopt in building their solutions. Today is one of those sort of combination topics where we introduce a very useful technology to make Ethereum contracts upgradable, but also we will show you how to use that within the Kaleido's context. So within Kaleido, just a very quick introduction of what Kaleido is, and we'll dive into the main topic. So Kaleido is the blockchain business cloud. We focus on making it very efficient and radically simple to adopt blockchain when enterprises need to come together and build a decentralized network to make their business transactions more efficient and to make cross-organization transactions and data flow more trustable and secure. We're the industry's first full-featured full-stack platform. So blockchain itself is the enabling technology where it gets a lot of enterprises and companies, both big and small, thinking how to make things more efficient than they are today. But quickly they realize it's actually pretty difficult to run a blockchain layer that's gonna be very robust, have DA and HA and DR, and have robust operations. So very quickly they realized they don't want to sink their IT resources on the blockchain layer itself. They rather want to use a partner that's specialized in doing this, and then so they can focus on building features that matter to their customers. So Kaleido is built to allow our customers to start very quickly to explore the technology, build a POC, and then take the next step of building a pilot project, onboard some members and try this out to see if their new business model works out as they expected. And finally, on the same platform, they can quickly go into production. And we certainly have many customers that's been in production on Kaleido for many years. You can see on this slide many familiar logos that's been building and running their new IT, decentralized IT systems on Kaleido. Kaleido is unique in that we treat blockchain as a core piece, but it's also at the same time a pretty small piece when you look at the final product that is built on blockchain. The rest of it, almost 90 to 95% are beyond blockchain itself. It's either middleware that keep things flowing from one organization to another in a secure way, having decentralized document storage. So documents can be secured, but also can be exchanged among the members. Just to give an example of some of the features that are needed to build a real production quality blockchain system. So our platform is designed so that not only you get the blockchain layer very easily and quickly and can run it day in, day out without having to think about it, because we have SLA when you sign a contract with us to keep it up, 99.9. So they can focus on building their own stuff that they're specialized in for their industry. And this is a quick overview of the Kaleido stack. As you can see, blockchain is the foundation, but it's got many layers above it, whether that's making transactions management easier and notify the events from transactions on the blockchain out to other systems, whether it's to connect different members with a secure messaging bus or connectors to other IT systems in the backends, or on the application layer using cryptographic techniques to do highly advanced signing or encryption or zero knowledge proofs so that they can build the new novel way of securing their data and doing data exchanges. So that's a very quick overview of what Kaleido does and provides. We are an enterprise level and quality platform. So we have ISO certified on 27001 and 17 and 18 for cloud providers and PII security. And we have many features that are very friendly to enterprise IT checklists for security and onboarding purposes. So with that, I'm gonna transition to today's topic, upgradable smart contracts, what they are, how they work under the cover, and how to use that with Kaleido. So first of all, some background on Ethereum smart contracts. Different design than some of the other competing platforms in the enterprise blockchain space that may offer upgradable smart contracts or similar technologies. Ethereum smart contracts are immutable. The contract code itself is saved on chain and is protected by the blockchain itself. And as soon as you deploy smart contracts to Ethereum, you can never change them. Even if you have exactly the same code deployed again on Ethereum, you get another unique instance of it, and you get assigned a unique address. So this is very essential to the Ethereum design. Another part of this is states, which is the kind of data, transactional data produced by smart contracts when they process transactions. States are managed on a per contract basis. So every contract is responsible for a portion of the overall world state that make up the transactional data and history for each account. So given both, what you end up is a same smart contract code. Once you deploy it multiple times, you get separate instances, each given a different address, and each of them will manage a different state tree. As you can see in the overall state tree for the entire blockchain, each contract manage a portion of it, and a different instance of the contract has a different portion of the state tree to manage. And as you can see, the first instance and second instance came from the same code, but different deployment. And the third instance came from a different version of the contract. So maybe you have to do a bug fix, or you want to introduce a new feature to the blockchain contract. So your contract code itself changed. And when you deploy that new version, you again get a new version. So basically, every deploy results in a unique address, and there's no way to sort of make an update to the code and still inherit the state from the previous deployment and sort of continue from that previous deployment. So this is by design because, as you remember, Ethereum came out of the mainnet deployment and token launches or other kinds of crowdsourced projects is the main use case scenario they have to address. And it's kind of essential for smart contracts to not change after they deploy, because once you've done the token launch, you've got many investors buying into whatever smart contract idea you have publicized. And if you make a change to it, or even a significant change under the cover without changing the address, the investors may not even know what's going on, and you will have changed the fundamental business model that they were investing in. So it's kind of essential for smart contracts to be immutable for that kind of model to work. But at the same time, as we explained earlier, this is also a huge inconvenience for developers when you have to go through the life cycle and evolution of a real-world decentralized app, because there will be bugs, and there will be bugs that needs to be fixed, and there will be new features that you'd like to introduce based on user feedback. So what you would have to do, because the contracts are not immutable, is you kind of have to deploy the new contract and migrate the existing state from old contract to the new contract. And in this process, you need to freeze transaction processing on the old contract while you're doing the migration to the new contract. So it's a pretty cumbersome process for any developers and operators to manage, and it's not a very good user experience. Luckily, there's been a lot of experimentation that's being done in the past few years to see, can I make contracts upgradable? The answer is obviously yes. There's been a few patterns that are pretty popular. The most popular pattern to make a contract upgradable is through proxy contracts. And if you want to read more about how this works, you can follow this link, or you can Google proxy contracts OpenZeppelin. The OpenZeppelin team, as well as other teams like Gnosis, I think there are a number of other very popular projects on Ethereum that are using this pattern to make their contracts upgradable through proxies. So now let's take a deeper look at exactly how proxy-based smart contracts are upgradable. So as we talked about, there's a Solidity code that gets deployed. And the Solidity code is responsible for both the logic of processing the transactions and generating new states to make state transfers from old to new, but also responsible for saving, maintaining the storage of the data. So the idea of breaking away from this monolithic pattern to make contracts upgradable is we want a separate contract to manage the data, and another contract to be hosting the logic. this way, because when you need to make changes, you tend to make changes to the logic, but the state itself tend to change less. But even if you have to change the state structure, so the storage itself needs to be upgraded, there's a way to make that possible on the smart contract that manages the storage, so that you can modify the structure of the storage without breaking compatibility. So the general idea is I will have one contract that manages the storage. We call it the proxy contract, and the separate contract that will be doing the processing. And from one version to another, you will be modifying the logic contract. So your new processing logic can be deployed, and the proxy contract can be redirected to the new version of your logic contract. So that's the general idea. How this works in more details is something like this. So EVM defines Ethereum virtual machine, defines a very useful construct called fallback function. It's a function that will be called if a request asks for a function that this smart contract does not have. So it's basically falling back to this fallback function if the smart contract says, I don't have the function you asked for. The EVM says, well, do you have this fallback function? By the way, the fallback function is an optional thing. A smart contract can choose to implement it or not implement it. But if it does, then EVM will say, okay, if you don't have the specific function the transaction is asking for, but you do have a fallback function, I'm gonna just call the fallback function. So it's called fallback because if everything else fails, call me. This is what EVM will do. So in this example, there's a smart contract instance at this address AA2F323, and the request came in wanting to call this contract function mint token. But if we look at the Solidity code of this contract, there are only two functions. One is constructor, the other is fallback. So EVM says, okay, you don't have this mint token function, but you do have a fallback, so let me call the fallback. So this is sort of the basis of how the proxy of the upgradable contract pattern works, is that the proxy contract is the one that implements the fallback. Because why this is necessary is this allows the proxy contract to support any function calls. Since the fallback is the one that gets called when nothing else works, this allows the proxy contract to say, I can take care of any function call, and you can feel free to throw at me any request. I'll take care of it. But for the proxy contract to actually be able to process a arbitrary function call, it needs help from implementation contract, which holds the actual implementation of the requested function. So in this picture, we see that the request arrives at EVM, let's say still mint token. EVM looks at the proxy contract first and say, okay, I'm gonna call fallback since you don't have that implemented. And the proxy contract just need to redirect that request and say, okay, you asked for mint token. The implementation contract that I know about just so happens to have this mint token function implemented. So let me just go ahead and redirect this processing request to the implementation contract. And then it'll be properly processed, and the return value goes back to the proxy contract and goes back to the client. And obviously, this makes the contract upgradable because from the client's point of view, it's dealing with the proxy contract. It doesn't really see the implementation contract because that's implementation detail behind the proxy. So the client is asking the proxy contract to do the processing. And now if you upgrade your implementation contract to a new version so that you fix the bug in mint token, but you can also introduce a new function. Let's say a burn token is now introduced. All of a sudden, the client will have the updated processing from mint token, but now is also able to call burn token, still going through the same contract on the proxy. So the key is the proxy contract never changed, still processing transactions on the same address. So the client doesn't need to know about a separate address in order to get the new processing logic. So this is how upgrade contracts works in general. Another important aspect to mention here is even though the actual processing of the transaction is done at the implementation contract, the state that resulted in the processing is maintained by the proxy contract. So just think of the implementation contract sort of as a library that's being used by the proxy contract. It's all happening, all the processing is happening within the context of the proxy contract. So the state is maintained by the proxy contract. This is why when you upgrade from version 1 to version 2, you can pick up where you left off and can inherit the same state that was produced and managed by version 1. And you can continue to evolve the versions of your implementation this way, and the state will continue to evolve linearly. So, okay, so that was sort of the theoretical portion of how smart contracts can be upgraded using this proxy pattern. Now let's take a look of a real example and how you can use Kaleido to deal with upgradable contracts. So the first portion of the demo, we will deploy a implementation contract. We have a version 1 of it. And the version 1 will have a set function on it. We'll deploy that first, and then we'll deploy our proxy contract. And the proxy contract will have this fallback function implemented. And then the proxy contract will be initialized to be pointed at the implementation contract, version 1, so that a set call can be invoked on the proxy contract and be processed by the implementation contract. So let's look at that portion of the demo first. So we're in Kaleido here. I have a Ethereum network based on Quorum. We're using Raft as the consensus mechanism. Typically, we see our customers use IBFT more often because it's a more robust consensus algorithm, especially when you have when you want to build a decentralized network instead of trusting a central party as the leader, which Raft is based on. But because Raft has pretty quick block period, just for the speed of the demo, we're using Raft for this session. I have 4 nodes. One is the system monitor and 3 user nodes. That's a good That's good size for a raft-based network. So we have at least a fault tolerant of single node failure. And first thing we want to do is we want to deploy our implementation contract. So if you go to GitHub Kaleido, you can look at, I think it's called examples, samples upgradable contracts. So this is a public repository that all the code we're gonna use today is here available, so you can follow along at home yourself. So let's take a look what we've got here. So our version 1 contract is pretty typical of a hello world level smart contract. It's got a single set function that can process transactions, and it basically does a quick check and then save the data in storage and then publish an event. It's also got a query method to read the data back out to the client. Notice this special interface that it's implementing. It's called initializable. So this is a unique aspect of upgradable contract. Remember back on the slide, we need to do this initialization step for the contract, for the proxy contract to initialize the implementation contract. But this will have been after the implementation contract has been deployed. So the constructor itself will have been invoked during contract creation. However, we want to give the proxy contract a chance to initialize the implementation contract. And that can't be done through the constructor because constructor is only called by the EVM. So we want to have a different way to make that initialization possible. And that's done through this initialize interface. It implements this simple interface function called initialize, and you can define a value yourself. And there's a modifier on it called initializer that's defined by the interface. So this is sort of the hint to the proxy contract to say, this is the function to call when you want to initialize the implementation contract. Other than that, this is a very simple smart contract. So let's go ahead and deploy that to Kaleido. So you want to go back to your network. We already have a network defined with a couple members, and we have a single environment defined in it. And of course, you can create as many environments as you need. Each environment corresponds to a separate blockchain network. You can have one for dev, another for shared dev, another for user acceptance test, and another for production. So you can build a pipeline. Right now, we just have a single environment in there. So we want to go to the shared assets category and find contract projects. If you're familiar with Tech Tuesday, we've had previous sessions that specifically focus on smart contract management within Kaleido. So I'm not going to go into much details there. We're going to just create a new contract project to manage our source code and compilation. We support both Ethereum and Corda. So for today, we're going to have an Ethereum project. So demo, upgradeable contracts. we offer different ways to upload and manage your contracts. You can give us the source code and we can compile it for you. And you have two different ways to give us the source code, either point Kaleido at a GitHub a URL where your Solidity exists. That can be a public GitHub repo or even a private repo. Or you can just go ahead and upload the source. And in both cases, Kaleido will do the compilation. Or you can say, I've already got ABI, I've already got the bytecode. I'm just going to go ahead and pre-compile and upload that. To save time, we'll just go ahead and upload our compilation. So we'll create a pre-compiled project. And now let's go ahead and upload our first project. So the first compile is going to be simple storage v1. And I've already got the truffle build results. So the ABI is going to be from v1 JSON. From here all the way to here. By the way, you can get detailed instructions of doing all these steps in the README of the project. Go ahead and paste this. Next is the bytecode, which is here. When you upload the bytecode, depending on your compiler, you may or may not get the 0x prefix. Make sure you always have the 0x prefix in there. Otherwise, the compiler will complain. Kaleido will complain. Finish. Oh, looks like we have uploaded this already. So I think what we need to do is let's just recompile it to something slightly different. Maybe we'll eliminate the emit so we can compile it again with a different bytecode. Okay. If you didn't catch it, that error that you saw earlier was saying that we've seen exactly the same bytecode for this project. So are you sure you want to do that? So we want to generate a different bytecode from a new compilation. So let's go ahead and do this. We'll just do a truffle compile. All right, cool. So now we've got both of these modified solidities recompiled. So we should have a new ABI. So let's go ahead and repaste this. And a new bytecode. All right, so now we've got our first contract ready to deploy. So note that this is managed at the network level, which is, it's a shared resource by all the members, and it can be applied to any environments. So what you want to do first in order to deploy this is promote it to a target environment. We're gonna have just promote it to the demo environment. And remember, we're deploying this instance so that it can be used by the proxy contract. We're never gonna use this implementation contract directly. So we don't really need a RESTful API for it. So we'll skip this step. We don't have to give it a friendly name for it, since we don't care about this, this API instance. So we'll just promote it. So now this contract is available in my demo environment. Let's go ahead and deploy it. Deploying this to Kaleido is very simple. You just say deploy instance, and because we generate RESTful APIs from the API that was uploaded earlier. You have a very simple RESTful API to both manage the instances, but also to interact with a deployed instance. So the first thing is we want to deploy that first. And to deploy it, we just have a post request that we need to call. There's really no input that we have to give. We just say, go ahead and post with an empty body. And boom, we have our first contract deployed, and we've got a contract address. At the same time, if you go to Data Explorer under your environment and you go to Smart Contracts, you will see the new contract instance that was deployed just now, which is 3.1. So that is deployed. Remember, the second step is now let's go ahead and deploy the proxy contract. So go back to the contract projects. And now we need to add the compilation for the proxy contract. So new compilation. We're going to call it simple storage. Notice that I'm giving the proxy contract just simple storage without the version, because this is the proxy, a name for the proxy that will never have a version change, because all the version changes are happening at the implementation level. So, okay, so now we need to give it the API. So let's think about the API. The API on the proxy contract, obviously we have an API that's compiled, that's from the compilation. So let's first look at the proxy contract. It's very simple thanks to the wonderful work done by the OpenZeppelin team. They've got really useful proxy contracts that are ready to use. So we have, we just need to inherit from the admin upgradable proxy superclass. And it takes three parameters, the logic, or it takes three parameters, logic, the sender, and the data. And two of them are taken from user input. So that's all we need to do. And if you're interested, the proxy contract implements the fallback that we talked about earlier. So let's take a really quick look at it. So admin proxy implements from upgradable proxy, which then implements base upgradable proxy, which finally implements the proxy. And this is where the fallback function is implemented. And this is what the fallback function looks like. It's a special function that doesn't have a name, doesn't take any parameters, and implementing it usually takes an assembly code. So this is basically what it does. It pretty much just delegates all calls to the implementation contract. And delegating that makes this call. So this is assembly level code that's invoking a native opcode. So delegate call sort of calls a library that's a target smart contract, and all the result is saved in the main contract. So using this call, the result comes back and handled by the proxy contract. So that's why the storage layer is managed by the proxy contract. And implementation, this will be the address of the implementation contract we just deployed for the V1 version. Okay, so if you think about this, the API of the proxy, obviously will have all of these to do the initialization, to do the redirect. but it also needs to have the API of the target implementation contract. Namely, we need to have the API of the simple storage merged with the API of the proxy itself. So that's sort of the special step that's required by the developer to merge the API from here with the API from here. So you just combine the JSON structure together, and that's been done for you. It's saved in the repository. So this is the merged API for V1. So let's go ahead and copy this. And as you can see, it's got functions defined by the, all these are functions defined by the proxy contract itself. And then on the bottom layer, there are functions defined by the implementation contract. So copy this and then plug this in here for the proxy. The bytecode, on the other hand, is just a bytecode for the proxy and nothing else. So we will find our Kaleido proxy and find the bytecode here. And that's it. So this is the special step you need to be aware of when you deploy the proxy contract. Again, bytecode is the simple bytecode from the compilation of the proxy contract itself, but the API is a special by combining API of the proxy contract plus the implementation contract. Okay. Okay. We have this too. So we need to recompile the proxy. We need to somehow. Let's see, how do we? Let's go ahead and make a small change to the proxy. Let's see what we can do. Maybe we'll add a storage variable that's not going to be used. Just go ahead and add a storage variable. Okay, that way we can get a new bytecode. Go ahead and do a compile. All right. So let's try again. New bytecode. Over here. And let's plug this in. Simple storage, bytecode, API. All right, cool. So we've got our proxy contract uploaded to Kaleido, ready to be managed. As before, we're going to promote it to our targeting environment. And because this is the actual contract we want the client to interact with, we want to give it a friendly path for the gateway API. So we're going to just call it simple storage. That exists. This is the test run that I was doing earlier. Has the same name, so we're going to call it slightly different with a prefix. Less than 20s. Simple start. How about this? Simple demo. Still less than 20. Simple demo. How about now? Good. Okay. got our new API gateway. So all the APIs on this smart contract are available at this API path. So now I'll go ahead and deploy this. Okay, so this is a special step because the deployment of the proxy contract takes two parameters. One is obviously the address of the implementation contract it needs to know about. So let's go ahead and get that. So I'm gonna log in to another window, and this is the smart contract that just got deployed. Copy this address, that's the implementation contract. And this, the data is a special parameter that takes a few things. This needs to tell the proxy contract what is the target initializer function it needs to call on the implementation contract so that the implementation contract can be initialized when the proxy is created. So to get that, what you need is you need to do this. It's a hex string that represents a call to the initialized function of the target implementation contract. So this is basically, a spec for the proxy contract to invoke the initialized function on the implementation. So we need to do this and get the get the string. So let's go ahead and get Web3, create an instance. Doesn't really matter what the local host is. We just need the instance of Web3. And then we're gonna call encode function, passing in the name of the function and also the initial value we want the initialize to call. So that's the result of the spec encoding, and we give this to the proxy contract. So now the proxy contract knows how to initialize the implementation when it gets deployed. So now the proxy contract is deployed. So as of now, we've got the proxy contract fully initialized, pointing at the implementation. So in theory, we should now be able to call functions on the implementation through the proxy. So let's go ahead and do that. Again, Kaleido has really powerful RESTful API support because we have given Kaleido the full ABI. It's able to generate a RESTful API. So now we can use it to interact with the smart contract. Remember, this is a combination of the proxy interface itself as well as the interface of the target contract. And we want to use the get and set. Those two are the actual function defined by the implementation. So let's first do a get and see if it works. We expect to see 10 because that was the initialized value on the target contract. So, so this is a special aspect about the proxy in that it doesn't allow you to use the same account that deploy the proxy to interact with it for normal functions. This is for security reasons. So we have to pick a separate account. So you can do that by going to this widget and select a different wallet. So you can pick any wallet you want. If you have HD wallet, if you have a Kaleido fully managed wallet, or even the cloud HSM based wallet. Right now, we just have a bunch of node built-in wallets. We'll go ahead and pick something different than the one we deployed the proxy with. So we'll pick the first one. And now go to the same and out again. So indeed, return value is 10. So this means our proxy contract is successfully connected to the implementation contract. So now let's go ahead and send some transactions. The set method is defined by the implementation. We'll use it. And let's go ahead and change the value to 20 and execute. So remember, this is all interacting with the proxy contract, but calling the implemented functions on the implementation contract. So we just got the value changed from 10 to 20. And let's do another get and see if the value is updated. Indeed, value is updated, so it's properly committed to blockchain. So now, let's go back to the demo scenario. We've gone through this flow, so we proved that the proxy pattern really works. Remember, the proxy contract doesn't really implement anything, but we still went ahead and call it to process a set function call, and that worked perfectly, as well as the get. Both are implemented over here. So now let's go ahead and upgrade our target contract. We have a version 2 of the contract that introduced a query method that didn't exist in version 1. So let's go ahead and deploy that. Going back to the smart contract project, and we'll upload the version 2 of the simple storage. So it's going to be simple storage v2, and the API will take it from here. API, this is compiled by Truffle. Notice the query method that's new in v2, and the bytecode. Okay. Finish. Now we've got this ready to be promoted. Again, we don't care about the API on this, so we will skip the endpoint friendly name. So now it's available as well on this environment. So let's go ahead and deploy. Again, it's a simple post without any parameters. So deploy that. Okay, cool. We've got it deployed, and the address starts with AC0B. So now, if we go to Data Explorer, go to Smart Contracts, we can see AC0B is now detected. And now let's go ahead and copy this address. So next step is we need to reinitialize the proxy contract to switch from version 1 to version 2. And this is basically a simple function call on this proxy contract. So let's go back to the gateway and focus on the simple storage, which corresponds to the proxy contract. Go to its API, and we need to call this function implementation, or actually update 2. Update 2 tells the proxy contract, here's the new version of the implementation, switch to use that instead. So let's go ahead and plug in the new address of v2. and executes. So it's been committed properly. Status is 1, the success. So as of now, the proxy contract has been upgraded to point to version 2. So in theory, if we call a get, we should still see the last value we committed with version 1. That should be 20. Okay, again, we need to switch to a different address when we call non-admin functions. So let's try again. Get, try it out, execute. Okay, 20, good. So basically, this proves that after the contract upgrade, the state from the previous version has been properly inherited, and we're picking up where we left off with version 1. And also notice that there's a problem. We don't have the new function that's introduced in version 2, because we still have the same version of the API that's corresponding to version 1. So there's an additional step we need to do to update the API. So we want to go to simple storage and say, hey, we've got a new version. Let's go ahead and upgrade the API. And remember, the new API really just introduced this method. So we'll copy this. So that's the net difference to, well, actually, just to be on the safe side, let's go ahead and use the merged one that has the new function. So again, you can find the merged API in the repository. So we'll copy the whole thing and just upgrade everything here. So once you save it, remember this is the change on the shared project level. It needs to be resynced to all the environment that it's being deployed to. So we'll do a resync, and that's all it takes for the environment now to have the new API. So now if you go to the new instance, and let's make sure we select a different wallet. And where's the, here, see the query? This didn't exist before, but now that we've updated API, the API has been regenerated based on the updated API. Now we have the new function in V2. So let's go ahead and call it and see if it actually works. Yep, indeed, it gives us the value, and this is because V2 is now in effect after the upgrade. Just on the safe side, let's make sure we can still process transactions. We'll do another set and update to 30. Execute. Looks like a success. And just to query again, and 30. So this wraps up the demo. You can see a full end-to-end flow of deploying smart contracts with the upgradable pattern, and you can evolve the implementation from version 1 to version 2. So Kaleido allows you to update. It's really simple to use this powerful pattern. So now you can have upgradable contracts. So to wrap this up, you're welcome to visit Kaleido.io if you haven't done that before. We have perpetual freemium starter plan. that you can use to start for free. There's no charge, and you can explore pretty much everything Kaleido has to offer. There are a few highly specialized features that issue might have or questions you encounter. So with that, let's see if we have any questions from the audience. There seems to be one QA. So the question is, what is it that ensures the fallback is not used as an attack or method of hacking? So that's a good question. When you call a fallback, there's a limit on the gas spend. So if you want to just spam the smart contract, there's really no stopping you from doing that. But understand you have to pay gas to do that. So the attack vector is exactly the same as any smart contracts that's deployed to public Ethereum. And in the private deployment, it's a little bit different because if you are using these RESTful layer, or even if you use the JSON RPC layer on the node directly, there's rate limiting on the API level that we enforce, so that unless you have a paid level that gives you a large capacity node, if you are just running a smaller node, you are limited by a API count per second rate limiting policy. So there is a bit of protection there. In addition, all the endpoints of Kaleido nodes are protected by strong credentials. So, a random person would not be able to attack your node. So even if you have fallback functions, I guess obviously you want to implement your fallback function properly so that it doesn't get into spending a lot of unnecessary cycles when there's a request for a function that doesn't exist even on the implementation. So if you look at the implementation by OpenZeppelin, you can get some hint of how that is done in here. You basically want to have a fail fast mechanism to shortcut if the method doesn't exist on the implementation contract. Don't know if that successfully addressed the question. If you feel like we need more discussions, feel free to type in more in the QA, or if there are other questions, we can discuss that. You can always reach out after the session through a ticket, and we can discuss more in depth